I need to record. Okay. So what we'll cover, first of all, indexing, what it is, why it's necessary, and how to make it faster. And then eventually, not so much today, we'll start talking a little bit about Google's indexing system itself, the Google specific details. All right, so we'll start off talking about indexing as a general concept, and then we'll eventually get into how Google does it. Okay, now, as anyone who's used Google knows, Google is fast, right? Typically, when you run a search on Google, you get the results back in about half a second, right? You get the first page of results. Now, if it's an unusual search, it might take a second or two. The longest I've seen for a conventional, first page for a common search is like about 2.1, 2.2 seconds. And of all things, it was for movie listings. And I don't know why it took so long. You can also see search results start taking a really long time if you dig deep into them. On occasion, you can kind of make Google time out, because if the delay gets long enough, it'll kind of quit. So let's go ahead. We're going to try to do a test with that. So I'm going to do something I haven't done in a long time. I'm going to do a Google search for, what shall we do? UIC IDS 355 Lundquist fall 2011. This was a thing I used to do back when. Okay, but I'm going to go, so the first page, about half a second, 0.51. I'm going to, oh, I'm not getting more, damn it. Sure, omitted results, why not? Ooh, now I get more pages. Yo. Oh, am I? I'm not muted, you just can't hear me. Yeah, that's fine. I'll do it, thank you. If the sound is missing, try logging out and back in. That usually fixes it, usually. All right, I'm gonna see if I can make Google fail though. Oh, still it's only 2, what the hell? No, am I over here? No, I had more pages, damn it. All right, I'm gonna try another one. Give me the name of someone famous. Ryan Reynolds, okay, I heard Ryan Reynolds. Okay, and we'll do 2016 and something else, movie. Yes, okay, and we'll throw in the word "the" just for no good reason. And this will get us a lot of things. Now the first batch of stuff, that happens pretty fast, right? But the next 0.61 for the second one, 0.64, you see it's creeping up. Ooh, 0.67. 0.74. See what's happening here? Google wasn't 0.88. Google wasn't expecting to have to work this hard today. 0.82. Oh, down a little bit. Okay. Let's see. 0.79. I'm impressed. Google. 0.8. I want to crash it though. 0.85. Come on, you can do it. You can fail. 0.91. 0.94. Come on, you can do it. 0.96. Ah. Okay. Ooh, 1.08. I know. This is exciting. This is like watching a 1.01. This is, oh, that's it. All right, I'm going to go all the way to the end. 0.89. Come on, you can do it. 1.07. A couple more. Well, we're going to see. It's like the same thing, right? If you like go all the way to the end of your Facebook feed, eventually it starts taking a 1.14. Oh, good. We could fail it. 1.08. When you go all the way to the end of your Facebook feed, sometimes it kind of quits. 1.19. 1.18. I know this is a bit silly, but we're doing it anyway. 1.2. I just want to see if we can make it crash. 1.2. But this is like 1.33. All right, we're getting there. The practical stuff, right, is that even for like this oddball stuff that Google wasn't expecting to have to bring up, 1.36, they're still doing it pretty fast. 1.41. Why are we doing this? I have 1.36. All right. Maybe I'm just gonna Google, I'm going to jump ahead a little bit. I'm going to try to give you a pass. Ooh, 1.52. It gets a little worse, you know. All right, let's see. 1.76. 1.88. I know, the suspense. 1.92. I at least want to get it over 2 seconds, right? 2.01. All right, Google, you win today. Good job. All right, it was a fair fight. I know. Okay. So anyway, that was just a little bit of practical whatever. So unusual searches, or if you're digging really deep into it, might take a second or two, as we saw. Okay, but in general, the search results for the things that most of the time Google serves up the good stuff on the first page or two, and you get it in about half a second. Now, this is especially impressive because data keeps on growing, right? 20 years ago, remember we saw our little graph and there were like maybe a few million websites. Now there's a couple billion. Pages were a lot smaller. They didn't have as many web objects. There weren't as many users. All that kind of stuff has made it really hard to keep up. So the analogy I used this morning, 1991, the internet is like a very neat and orderly garage, right? If you want to find something, everything is in a drawer that's properly labeled. You know what all drawers are there. You know what's in them, right? There's not much, and any object that exists, you kind of know what drawer it ought to be in. 10 years later, right? Even in 2000, the internet is not, but by 2000, the garage is, number one, 1,000 times bigger, and on top of that, there's a whole lot of things stored in that garage that you don't really know what drawer it ought to be in. It could plausibly fit in several different drawers, and you don't want to have to keep multiple copies of everything because that's wasteful of space. So it gets really hard to find what you're looking for without some special search technology. 20 years after that, which is basically where we are now, the garage is like 1,000,000 times bigger and has all these problems with data being hard to sort. But on top of that, there's always a whole bunch of people in that garage getting in your way whenever you're trying to do anything. Okay, that's basically the problem that Google is doing with. Again, pages are harder to sort. There's more pages. The pages themselves are more complicated. Google's dealing with a lot more search traffic. Okay, but they're still doing a remarkably good job of keeping up. And the way they keep up is, of course, through indexing. So remember the way indexing works. Google matches search terms to web page content, and the core element is text, right? So when Google's building the index, it has this massive list for any search term that might come around. It has a list of all the pages on the internet that contain those terms. So this is a very small scale example of what might go on there. So suppose you have the three words syzygy, zygoma, and zizaba, and they're each stored on a few pages around the internet, right? So if, for example, somebody does a search for syzygy and zizaba, you can see that that's stored on pages A, and they're also both stored on pages C, and one term but not the other is stored on some other pages. So when the search results come back, presumably pages A and C will be near the top, and the other pages will be, not near the top. Okay? That's the idea of how it works. There is an index. The index shows what terms occur on which pages. So whenever a user enters search terms, Google can very quickly retrieve the pages containing them because it's already done that work, right? It doesn't need to scan through 1 trillion different pages and find out what's where. It already has an index entry that says, oh, you might be looking for these pages, okay? And once the pages are selected, Google applies its ranking algorithm to determine which ones get delivered. In this case, the number of matches is very small, but as we saw last week, some popular searches can return, 10 or 20 billion matches. Obviously, Google's not going to deliver all of those, right? Nobody has time to plow through like 20 billion search results. And the way Google builds the index is, remember, it has these browser applications, these agents called Google bots. They go around to different pages, they scan the web pages. When one of those finds a web page, it captures all that text from the document, sends it to Google's indexing system, and says, oh, I found this page, it contained these words. If necessary, add this page to the index entries for such and such, terms. Okay, that's the one slide summary of indexing. Okay, now why is indexing necessary? Well, the short version is that a relatively small amount of overhead saves a lot of processing time. Okay, and we'll start with the human example for books that hopefully you're all familiar with. So, suppose you have a very large stack of books and you wanted to find out which, if any, reference Charles Babbage. Charles Babbage is a significant figure in the early history of computing, but you don't need to know that. In fact, we're going to assume that, like a computer, you have no idea who he is or how his name might be, suggested by a book title. For example, if you had a book about the early history of computing, you might very reasonably expect to see a mention of him in there, right? Whereas if you had a book about, I don't know, Freddy, the happy alligator, that's probably not going to reference him. Anyway, so two approaches. Number one, and both of these approaches will give you the results, right? It's a question of how much work you have to do. So the slow approach, of course, read each book from start to finish and note of any mentions of Charles Babbage, right? That would be kind of crazy. We would never do that in real life. What do? Well, each book has an index. Somebody already did that work in advance of going through the book and saying, oh, here's where this thing is mentioned, here's where this other thing is mentioned, and tabulating all of those and including them at the back of the book as an index. So the work was already done up front, but once that's done, it's very easy for subsequent readers of the book to go in and find what they're looking for. You can just flip through the index of each book, see if it references Charles Babbage. If it does, great. If not, well, I guess also good to know. Okay. Now, second thing, distributing. So a distributed system generally works in the way you have a big task and you break it up into smaller pieces and assign or distribute them over a set of machines, right? So the real life analogy, suppose you and your team of buddies are out raking leaves, right? You're trying to make some leaf raking money because this is the time to do it. And you go to a very large field, right? It would not make sense for one person to do the entire field by themselves, right? That would take many days and you wouldn't get it done and the snow would hit first. But instead, right, maybe you got a team of like 20 or 100 guys and you say, okay, we're going to divide this field into a grid. Everybody takes one grid cell, right? And you do that raking work within your grid cell. Same kind of thing with this distributed stuff. So imagine your stack of books is very, very large, right? Tremendously large stack of books. There's no way for any conceivable real-time purpose you're ever going to be able to scan through those yourself. And like most humans, you only have two eyes, right? In that case, even an indexed search might be too slow. If the stack of books is big enough, it takes a little bit of time to go to the index in each one. Even an index search might not be fast enough. So, solution, get a bunch of your buddies together, a task into a component small tasks. So, in real life, you have this gigantic stack of books, you divide it into substacks, give each one of your buddies a substack, you keep a substack for yourself. And then you search the indexes in those books. Now again, the total work remains the same. You still have one pair of eyeballs scanning through each index, but you get the results a lot faster, right? If you have one buddy and you say, here, you take half, I take half, the task gets done twice as fast. If you have 9 buddies, you give each of your 9 buddies one stack, you keep a stack for yourself, the work gets done 10 times faster, right? We can understand this makes sense, I hope. Yeah. Same thing with this distributed system, right? If you have a very, very, very large page entry, right? So we saw some stuff like money or sports could have like 10 or 20 billion pages. If you have one machine working on that, it's going to take a little while. You're not going to be able to maybe to keep up with that half-second speed. So instead, you break up that very large index entry, have it processed by a bunch of different machines in parallel. Each machine does a small portion of the total work, but the work gets done a lot faster. So the amount of total work remains the same. If anything, it gets a little bigger because you have to deal with the breaking up and the recombining at the end, but the result's much, much faster. Okay. Next thing, caching. So imagine that your search operation has become popular, right? You're dealing with all these books and you get phone calls coming in, people want you to do their search work for them. So it's become very popular. and you have millions of search requests coming through every day. Fortunately, you also have this attribute that a number of the searches are repeated, okay? And when a search repeats, that means you can store the search results. You can store the search results and retrieve them pretty much instantly, right? So if, for example, suppose you have one guy on your team who has a limited but photographic memory, and he can remember the entire set of search results for 100 different search queries, right? The sensible way to use that talent is to use his memory for the most popular queries. That way you make the most people happiest, okay? For example, if you have only 100 different searches that occur during the course of the day, he can handle all of them, right? This is basically just like cache. So in that case, we would say that the number of cache hits are 100%. So 100% of the searches can be responded to by the cache, right? Which means, number one, your response time is going to be pretty much instantaneous. That's going to make people happy. And number two, the rest of your system is available to work on anything else that might come down the pipeline. Suppose if there's 200 different queries. Well, your fast guy, he can process 100 of those, right? The other ones, the least common ones, they're going to be handled by the rest of your team. But because this one guy, your cache is basically handling a lot of the traffic that comes to your site, basically instantaneously, you know, maybe your number of cache hits is like 90, 95%. It makes it a lot easier for the rest of your team to handle these ones that need a little bit more customized work, okay? So same kind of thing. Google, obviously, if there are very popular search results, Google is going to either pre-compute them or cache the results so it can deliver them pretty much instantaneously. It doesn't want to do all these things from scratch all the time. All right. Now, of course, early on, Google did all of this indexing by search terms, right? By the exact terms that people used. And this works actually really well if they are pretty rare terms on mostly text pages and the number of pages having those terms is not that large, okay? And that things like web objects on the pages actually don't matter that much. So if the pages are all text and a lot of the search terms that people are using don't appear on many pages, then yeah, indexing by exact term matches is going to work pretty well. People are going to find what they're looking for with what's on the internet because there just aren't that many candidates. But of course, like we said, for 10 years or so, Google has been working very hard to semantically match the user's intent. What it does, it tries to figure out what the search terms mean and then deliver matching results for that, okay? So we're going to give an example. What's that? Do you need screen, screen, screen? This is kind of neat. This actually works. I don't have to flap this back and forth. So that's kind of, where's paint? That's surprising. This is my new university machine, and I'm using it because it's very portable. So that's a plus. Anyway, but I just wanted to give you a little understanding of the math behind things. So suppose Google represents the query results for by car as this line. Okay, you with me so far? We don't know how Google does that math. We don't need to know. We just know at the end of the day, they're going to express that as some line. Now, if the components are very different, right? So for example, suppose we have one search for by and another search for car. I'll do that here. And these terms are not collinear at all with this search result, right? Then Google is going to look at that and say, not collinear, these are very different queries, right? And the fact that they're very different query results means that justifies having by car be its own separate thing. That's the math of how Google recognizes this, right? So in the end, if Google says there are two sets of search terms, if they deliver the same results and people show the same click behavior on them, then they're functionally equivalent, right? Google's, you know, maybe they're different in some meaningful way, but as far as Google is concerned, as far as delivering content that people want, if people get the same results and they respond to those results in the same way, those terms are functionally equivalent. But in this case, they're very different, right? The lines are not collinear, they're almost perpendicular. So Google says, yeah, these are very different, right? On the other hand, if they looked something like this, right? If here was the one for car, and we'll do in red the one for buy. If they looked more like this, right, Google could say, oh, I get it. These are very similar, and we don't need separate things, right? We don't need some sort of separate unit for this because they are very, very similar. Buy car is probably not a distinct semantic unit. Okay. Anyway, so that's, again, if it helps you to have a little mathematical model in your head of how that works, then there you go. There was one. Okay. Now, indexing, of course, it can incorporate semantics by creating entries for these very distinct term groups or concepts, right? So, for example, if buy car turned out to be very significantly different from its two component terms, Google might create a whole separate index entry for buy car, right? If the words New York and city were very different than their individual components, Google might create a separate index entry for New York City, okay? And again, these things, they can be integrated into the normal search process, or they can be displayed separately through the knowledge graph like we talked about last week when we talked about 17th century scientists, right? So again, Google has a lot of flexibility on how it wants to implement this. But once it recognizes that a set of search terms means a thing that's very different from the same terms in isolation, then Google's going to say, yeah, okay, this is a separate thing. We can track it separately. Okay. And one way to do this is by considering how terms are used. So, for example, as humans, we would, or at least as English-speaking humans, or familiarity with, English language names, we would look at Charles Babbage or Babbage, Charles, and we would instantly recognize that that's a name, right? Sure. We say, yeah, it's a name, and we know the one is, just the name, and the other is Babbage Charles, like maybe you'd see it in a listing of names by last name. And we know that in a book index, we would expect to see Babbage, Charles, not separate entries for Charles and Babbage, right? Because Charles Babbage or Babbage, Charles is a semantic unit. It is very different from the two words separately. Likewise, as readers, we would also be able to see the difference between or Charles Babbage, which is part of a phrase, comparing probably another human to him, or versus Charles or Babbage. In that case, with the word or in the middle, we would instinctively recognize, oh, those are two separate things, right? And this really illustrates one of the limitations of just text matching, because it might consider those two to be equivalent, right? But they're not. They're not at all equivalent. This one, the first one, or Charles Babbage, clearly references the guy Charles Babbage. The second one, Charles or Babbage, clearly does not. And so if you're looking for Charles Babbage, you're not going to find it. Now, let's talk about this for a moment, some practical stuff. Why do book indexes list names, last name, first name, and not first name plus last name? Why do they do it that way? Yeah?
First names are more common than last names.
Because first names are more common, right? If you had a book that listed all the Charleses, you'd probably have a lot more entries than a book that listed all the Babbages, right? So at the end of the day, this is structured to make it easier for readers to find what they're looking for. Now, Google does the same sort of thing, not exactly like this, right? But Google has some tricks that they use. Number one, the popularity of a term is going to determine where it gets stored when the indexes are organized. So whatever pieces of hardware hold those lists, anytime Google has to scan through the list to find the index entry, if it's at the start of that list, right, it's going to be faster to get to. So things like, and again, this is a little bit beyond the scope of, I'm not going to ask you about this kind of detail on the exam, but just understand this kind of thing, that humans are able to find this easier. Google has some tricks like that itself. It doesn't use these exact same things, but it arranges the data in a way that the things that are more common are easier to find. It arranges data in a way where more likely groupings are given priority. So for example, if you enter in, search, search Charles, typing is hard. Okay. Charles Babbage, history of computing, right? Very quickly, Google is going to recognize this is a moderately popular search. This is a moderately popular search. These term groupings make sense. We might consider other combinations of terms, but we are basically going to prioritize those two because Google's system has enough data that it can recognize, which of those are popular and which aren't. Okay. Anyway, so yeah, Google has some of those same kind of tricks. And what goes into a typical index, right? The entire index, the index entries are semantic units. If you look in the back of a large book, right, you're not going to find just single words. You are actually going to find complete semantic units. So if it's like some old history book, there's going to be index entries for people, there's going to be index names for places, there's going to be index entries for significant events, right? And all those could contain multiple words. So again, the index entries in a book are very often going to be multi-word semantic units, right? Some groups of words with a specific meaning. Again, Google wants to do this too. Google wants to do the same idea in order to deliver more relevant search results. The only problem is it's tricky to do in an automated system, right? A human can look through a book and they'll recognize, if they're looking through some history book, they'll say, oh, the 30 Years' War, that was a thing in Europe. We know when that was, right? Or the Peace of Westphalia, they'll say, yeah, that was a treaty that they signed at the end of it. That's a human reading this with some knowledge would understand automatically that these things are significant. But trying to do an internet scale automated system to do this is a very, very different process, right? You can't have that human intervention. Anyway, so this is a big problem for Google. Another thing Google does, how it deals with common words. So normal users, Google does a pretty good job of delivering search results. So a normal user is probably not going to consider more than a few dozen pages and typically, or a few dozen results and probably many fewer, right? So, I mean, how often does it happen when we look beyond the first page of Google search results, right? Not very often. Most of the time, for what people are looking for, Google does a really good job of delivering results on the first page. So, in most cases, search engine only needs to deliver a very small portion of the possible matches, doesn't need to deliver them all. Another thing about that, very common words like the or and or it or he or she, right, or they, all those kind of words, they appear on very, 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 very many pages, right? The word the probably appears on almost all English language pages. So because of that, they're not going to materially differentiate pages. You can't say, oh, this page is a better match because it contains the word the. That's not going to work if they all contain it, right? Number two, it's a lot of extra work for the ranking effort. On the off chance that somebody includes the in a search query, right? Google has to do a lot of extra work to process that, and it's going to be wasted work because it's not even going to materially differentiate pages in the first place. And finally, the index entries for those terms are going to be absurdly large. So suppose there are 1 trillion pages that contain the word the. It's probably quite possibly a little bit higher than that, but suppose there are 1 trillion pages that contain it. The index entry, just considering the page references, so imagine every page reference has like some sort of 12-byte index saying, here's where this page is, in Google's system, not any of the data of the page itself, just where to find it in Google's system. for a trillion pages would be about a dozen hard drives, a dozen disks worth of capacity. Now, the money isn't the issue there, right? Because a dozen hard disks is not going to, or a dozen solid state drives is not going to cost Google very much. But just if it takes that much to store the locations, it might take several hundred, several thousand disks to store the actual data of those pages. And for what? For nothing, right? But it has to scan through all those disks every time it needs to find something. So Google's not going to deal with those very, very common words. I will show you a little thing though. So I remember when I first started, I did these demos in class, and I said, you know, Google doesn't index the words the, and so there won't be any difference in the results across pages. But as it happens, if I do Chicago Cubs, or do that search, I get some stuff. I get a knowledge card here about Chicago Cubs, official Cubs website, blah, blah, blah. If I do another Google search over here and I do the Chicago Cubs, I actually get slightly different results. I get this website right at the top, right? And as opposed to over here, I get some news articles. I don't know why. Google knows why. They have decided that, people who use the word the are searching for slightly different stuff. It doesn't mean they have the word the indexed. What it just means is that that's another factor that Google is concerned about in how the terms are co-located, or maybe in things that people are clicking on. My best guess is that people who are talking about the Chicago Cubs, they're older people, maybe looking for information. Sometimes, I don't know, maybe they're looking for historical stuff, whereas people that are just Googling Chicago Cubs, it's a materially different batch of people that are doing that search query, tend to be younger people. Just like, I don't know if you have parents that talk about going to the grocery store, they'll say going to the Jewel as opposed to going to Jewel. I don't know, my parents used to do that, but whatever, I don't know. Maybe it's just an old people thing. Anyway, so there are some slight differences, but the differences do not result from the index entry themselves, right? The is still not indexed by Google as far as I can tell, but you do get slightly different search results from them. Other stuff, I do have a bunch of links, this slide and the next one. So starting with this one, SEO, search engine optimization. The idea there is you try to get your page to rank high in Google search results, which are free, in order to drive more traffic to your site so people hopefully buy more stuff. That's what SEO is all about. And the article there talks about some stuff about words that Google doesn't index and words you should not, include on your sites if you want your pages to rank higher, stuff like that. If you're interested in any of that, again, very readable article there. It talks about that. Also, some more additional reading about semantic search and the knowledge graph. So some overview articles if you want to learn more about how semantic search works. Again, the core idea, Google wants to do a better job of figuring out the meaning of user search terms so it can deliver better, more accurate, more relevant results, right? Better results than you would get just with exact term matches. And all those basically talk about that, or the knowledge graph, how that works. The other one, Hummingbird. Hummingbird is the algorithm that Google uses to do this sort of semantic term matching. And it was, pretty neat when they introduced it about a decade ago. You can read some stuff about that. So what is Google Hummingbird? Ta-da. If you're interested in any of these things, by all means, I hope this is some good reading for you. As far as the exam, it wouldn't hurt you to know what Hummingbird is. Obviously, we're not going to talk in detail about how Hummingbird works. That would be a very advanced IT algorithm topic. But Hummingbird is basically Google's algorithm for delivering better semantic search results. Okay. Now, okay. So as far as Google's indexing system, now we're starting to talk a little bit about that. We can first consider the problem in the abstract, right? So each request goes to some cloud system, and we know the tasks. We have a rough idea of what Google has to do. We don't know how all the systems are designed or how the interfaces are specified, but we have an idea of what's going on. In fact, this is how Google actually intentionally designs their systems, because the systems are so big and so complex, it's not really feasible for design teams to have detailed knowledge about more than one. And number two, having these components be modular makes it very easy to change part of one without affecting the rest of the system. And in fact, Google does that a lot. Google is constantly updating parts of the systems or tweaking algorithms. And if it had to worry, oh, if we tweak this algorithm, it could like wreck the whole rest of the system, it'd be a lot more work to do that. So I'm just going to do a little picture here. We're going to do a quick example. And I have to do a little smaller size. I don't have, the one thing I don't like about this is I don't have nearly as much space to work in this. I'm going to have to do something. I'm going to have to change the screen size parameters. Okay. What? Okay. So over here, we have a user, which is us. And the user enters in some kind of search query. What it is exactly doesn't matter. But we have Google here on the other side. And what we know about Google is that we are going to enter in a search query. Dun, dun, dun. It's not easy to do this with a touchpad. And Google's going to send back the search results. Okay? Now, from a modularity perspective, we know everything on this side of the system, this is Google stuff, right? We can't peek in there and see how it all works. This is Google stuff, and this is user stuff. All right? So you know how your own stuff works. We don't know how Google works. Now, the first thing about modularity here, it's kind of a neat thing. Right? Google search works for a user regardless of hardware, right? Whether you're using a Mac or a Windows or a smartphone or a tablet, whatever. Hardware, operating system, doesn't matter. Browser, doesn't matter, etc. Right? All that kind of stuff doesn't matter. Oh, I will say end your connection, right? Doesn't matter if it's wireless, wired, whatever, cellular, because of modularity. All Google knows, if you have an IP address and you can run a browser and send the message to Google, Google can send the message back to you. Ta-da! This is great. We'll talk a little bit more about this before the course is over, but this kind of modularity is really important. Imagine what a headache it would be if every user had to somehow specify their system for Google, right? If Google only worked with a particular kind of machine or a particular operating system, or you said, oh, sorry, you're using Firefox. Google only works if you're using Chrome, right? That would suck. You don't want that. You want this kind of modularity in place. And the same thing works behind the scenes at Google. So, for example, the various processes that Google goes through, right? You enter in some search terms, Google is going to have to parse the query string, lowercase s. Basically break it into terms. Break it into terms. Because Google has to say, oh, you entered this long string of 8 or 10 search terms, right? How am I going to figure out what index entries that corresponds to, right? But once you have that set of search terms, you can take those and start retrieving pages, right? You can search index, scan page, send to index. Okay, and then you will get a set of matching pages, right? And once you've had this set of matching pages, you can take that set and you can rank them. Ranked results, okay, so you can rank all of them. So I'll say ranking algorithm. And once you have that set of ranked results, you can prune them and convert to web pages. So because remember, you might get millions or even billions of matches. And so then you get your subset that you're actually going to return. And then once you have that subset, you can convert them to, right? You can convert them to web page format. So you actually do some formatting on them. And then you have your real search results, which you can send back. Okay, so each one of these steps, in fact, has its own algorithm attributes or modularity attributes as well. So, right, this set of matching pages, all this does, it takes a set of search terms. There's a process where the index system says, oh, I have to return results for this batch of search terms. So it gets the search terms, it says, we have all these pages that match. You send along that subset of pages, somehow Google says, okay, we've ranked them, here are the top matches for that. You know, at some point, we're gonna prune that set of, total ranked results. Somehow those are going to be formatted. We'll get a subset. We'll take those subset of results that are just raw web page data at that extracted, but still that web page data, and format them into how you're actually going to see them on a device. So combine them into some sort of HTML format and send it back to you. And again, each one of those steps inside Google's system is a modular thing. It accepts an input in some standard format and returns an output. Now, again, don't take this as written in stone. We don't know the exact details of how Google does all this stuff. This is just a general idea of the processing that happens, okay? This should not be taken as some sort of literal truth. Google does this, but these are, generally the steps that Google goes through to deliver you the set of search results, right? It gets a set of search terms. It goes through a whole process to deliver you a set of search results, and each sub-process there is modular as well. Okay. So the design questions, obviously things like what tasks are required to handle the queries, what's the sequence of the retrieval process, what are the associated interfaces. Again, we don't have super detailed stuff about all this. This is kind of Google's special sauce. They don't want to talk about it in too much detail, but we have an idea of the steps that happen and the sequence they kind of need to happen in. Okay. Now, as far as Google's system architecture, think of it basically like Facebook. They have a bunch of data centers. Each data center is set up to respond to queries from a geographic location nearby, right? So it's its own little geographic region. Reason why it doesn't have just one massive worldwide data center, number one, if it did, traffic surges and system failures would affect everybody. That would kind of suck. And I have a link there from, a time when Google got hit by lightning a bunch of times and they actually lost some data because of that. Number two, just like Facebook, you want to keep locally relevant data closer to users to make it easier to deliver locally relevant content, right? Obviously, if, most of the users in North America are using English, there are probably substantial subsets of Spanish and French and minor subsets of other ones, but those are probably the big three. On the other hand, if you're on the other side of the world, you get other languages like Japanese, Chinese, Korean, Vietnamese, whatever. You have a bunch of different languages that other people are using that you're probably not going to see much of in North America. So it makes sense that, those data centers could each store a different subset of content. The other thing is delivery speed. The further away something is, it does add a little bit of delay time. If you're trying to deliver something to the other side of the world, that adds on maybe another 1/10 of a second or so to the delivery time, which isn't huge, but you'd rather have your results faster. The other thing, energy costs. So all of this that Google is doing, there's a lot of electricity involved. And I remember seeing a factoid once that Google consumed about 0.5% of the whole world's electricity. So, anything that Google can do to keep, local content local, this is going to be an important energy savings. On top of that, same thing about cyclical changes in what's relevant, right? So if you're just dealing with North America, what's popular at 8 p.m. in North America is likely to be the same stuff, more or less, that's popular at 8 p.m., right? AM, 8 p.m. is going to be the same stuff because it's all the same pool of users. But if you have one worldwide data center, it might be that during the day, you know, your traffic is dominated by North Americans, and it has one kind of content that gets to be very popular. 12 hours later, most of your users are from the other side of the world requesting very different content, which means you're going to have to constantly cycle through your cache and update what's there and update what's not there and bring it back the next day. It's going to be a lot of work to do that. Google would rather not do that much work. So there's multiple reasons why, just like Facebook, Google tries to cache store locally relevant content, you know, where it's locally relevant. Having said that, it's not technically impossible for Google to do this with one data center, right? One of Google's current data centers could probably handle the whole worldwide search load from like 15 years ago, because it's grown that much and the hardware is more powerful. But you know, just because they could do it doesn't make it a good idea. You know, it would not be the best way to structure this system. Right now, Google has about 30 data centers. Most of those are operational. A few of them are still in construction or being finalized, but the number about 30. Yeah, they have about 30. So now, what is a data center? Well, you might have heard of them. Basically, the way to think about it is a giant warehouse full of servers, right? Not really full of servers. If you see it, there's a lot of empty space in the room, and the servers are kind of centralized, and there's a lot of air conditioning equipment in place to help the electronics keep cool, even though it's working all the time. But yeah, basically, these massive warehouse type buildings with a bunch of server machines inside. Beyond that, the details are mostly hidden from the public. Yeah. Now, what is a server cluster? You might ask. Well, Google uses groups of servers to do the same kind of tasks, right? So any task that comes in, whether it's a search query or some other stuff Google has to do, typically those tasks get broken up into components. The different components get completed by sets of servers. So if you have a search query coming in that involves 20,000 index pages, Google really doesn't want to do that whole search process on one machine. It's going to take a really long time. Instead, it breaks up the task into, you know, possibly hundreds of subtasks and runs each one of those subtasks through a separate machine. That kind of parallel operation keeps everything going fast. All right, and by the way, the reason why they call it parallel operation, I'll do a picture because we need more pictures. Imagine if you have a big task coming through, right? Big task. And at the end, you want the results. Okay, but the task is too big to be completed quickly on one machine. So if you're drawing the flow of this, right, what's going to happen is your system gets broken up into a bunch of components, right? When you're drawing the line for this, all these are happening in parallel. So, you know, that's why it's called parallel flow, right? When you're drawing out the picture of how the action is actually happening, it's going to all look parallel like this. There you go. So in case, hey, why do they call this parallel? Machines operating in parallel. Ta-da. Okay. Anyway, functionally, this is very, very similar to a RAID device. Okay, I'll take a moment to talk about a RAID device, and I think we're going to call it a day, because this is where we ended up. We were done a little early. Whoop, we're done a little early. Okay, so imagine if you have a RAID device. We're gonna, what's that? Anyway. All right, so imagine we have some sort of RAID device like this. You guys remember RAID devices? When I talk about a RAID device, you remember what I mean? What? Yes? I'm not talking about the bug spray. What is it? Redundant arrays of inexpensive or independent disks. But you don't need to know what RAID stands for, right? What you need to know is that there's some user, right? There's some RAID device, and think about how it works on your laptop, right? If you want to retrieve a file, you don't need to tell the hard drive, you don't need to tell the disk drive, hey, I'm looking for this file and it's located at this track and this sector and this is where you go to find it, right? You just say, give me the file. And the disk drive somehow handles that, right? Same thing with a RAID device. If you want to retrieve a file, if you launch some I/O request, right? I/O for input output. Whoop. You make the input output or I/O request, and the RAID device handles the details, right? For example, if it's mirrored, if it's stored on more than one device, the RAID device is going to or it's stored on more than one disk, the RAID device is going to pick one. If the file is striped, right? If it's broken up and stored on different disks, the RAID device is going to say, oh, we'll get segment 1 from disk 1, segment 2 from disk 2, segment 3 from disk 3, right? The RAID device is going to handle those details. And again, this is very, very, very similar to how cloud works, right? Or how Google's system generally works. So imagine if you have the same thing. You're going to be a user down here, right? And you launch some request to Google. All you do, you send your request to Google. There is an interface that says, aha, you have entered some text, right? And then there's going to be a cloud. I'm going to draw a cloud. I'm going to draw a very nice fluffy cloud. What? We're going to fill that in. Is that fill? Yeah. Boom. We have cloud. Okay. And the nice thing about cloud, again, you don't need to know the details of where your stuff is stored. But when this request comes in, Google knows where to find it. Google says, oh, you want this email and you want this search result and you want, this other thing, whatever. Google knows where to find this stuff for you. Okay. So functionally, it feels the same way, right? A RAID device feels the same when you use it as an ordinary disk drive. Cloud feels the same as an ordinary disk drive in that sense, right? You send it a request. You don't need to know the details of what's happening behind the scenes unless you're doing really specialized technical work. But Google knows, and Google can connect you to it. Okay. So, again, this is what we're talking about when we talk about server clusters. Server cluster is just a bunch of different machines working together, to complete kind of related tasks, whatever those tasks may be. And functionally, it works a lot like RAID. All traffic happens through a shared interface, right? All the different users go through google.com, just like if you had multiple users connected to a RAID device, you'd all go through that same hardware interface there. The device itself, the interface directs those requests to particular machines, retrieves the results, and sends them back to you through that same interface. And generally speaking, behind the scenes, there's going to be some kind of parallel processing involved to deliver greater speed, right? Now, it could be that for Google, there is a search entry that's so small and obscure that it can be handled easily by one machine. There's only like 10 pages that match it. That could happen. It's rare, but it could happen, right? Likewise, if you have a RAID device that only has the files stored in one place, yeah, they don't need to do much work with that, right? But a lot of stuff requires parallelism. Okay, this seems like a good break point. We'll come back on Thursday. We'll finish up the lecture. And, I will announce some times. I'm actually busier than I expected to be this week because our dryer kind of shit itself, so we are having a new one delivered tomorrow. I was going to do review times this week, but I'm pushing them off to next week because of that, and I will announce times through Blackboard later today. Okay, but next week will be the time. All right. Now it's time to get lunch. Okay. Okay.
Are we gonna have like the actual final, or is our
Yes.
final going to be like YouTube instead? Like the YouTube
That will be
video?
the actual final. It's not going to be comprehensive. Is that what you're asking?
Yeah.
It won't be comprehensive. It'll be just the YouTube module.
Okay.
Yep.
Okay.
I have a question.
Okay.